Nobody is questioning now that we're living in a time of big data. Within just a minute, incredible amounts of data are being amassed. It's unimaginable, and it's even more than you know of. In any case, this has really inspired many people. The idea was that if you just have enough data, we would not need theory and science anymore. We would just have to look into the data, and the data would tell us to choose and guide us the way in a sense. So the question came up, can we now know everything? Can we understand the human body, brain, and personality? Can we now see what is wrong, fix the system where it's broken? And for such and similar reasons, one attempts to build so-called digital twins. That means highly accurate digital representations of everything, like buildings and cities, climate, weather, and people, including your health. Not general health of people, your personal health. Okay? And then the question comes up, can we now perhaps fix the world with a control room approach? Could we basically just amass all the data in one place in a giant data center, perhaps with the help of AI? That is at least the dream of those people who say the world is too complex to understand for human beings, and that's why we need super intelligence in order to basically get some order into this chaos of the world that we're now experiencing. And in fact, the military has been working on these kinds of concepts in several countries, and they have tried to build prediction machines for quite some years and have invested hundreds of billions into this. Most people don't know much about it. And then this happened. Geoffrey Hinton, the perhaps most cited person right now in the universe, who has worked on how to fit those digital twins. I mean, how to calibrate these models with a huge number of parameters. He suddenly dropped out from Google. Not only did he leave Google, he also warned of dangers ahead. So how could that happen? What went wrong? In fact, I think it couldn't work well. Couldn't work well enough because there are some fundamental limitations. Measurement errors, sample biases, classification errors, correlations are not causality, the computational limits, there are NP-hard problems for those who know what this is about. There's sensitivity, deterministic chaos, turbulence, the problem of overfitting, black box algorithms, learning algorithms don't always have to converge. There could be difficult to learn problems. Non-robust models, context dependence, ambiguities, undecidability, incompleteness, and some of that is really of great interest also to philosophy. Some of that is quite mathematical, and most people don't know much about many of those points, but they should before they invest $100 billion into something, right? So basically, I'd like to focus on this point, which is marked in red. In fact, what I want to say is digital twins are lacking complexity science. It doesn't matter much when it comes to buildings or infrastructures. It matters, however, when it comes to weather, climate, health, brain, ecosystems, immune system, and so on. And these are areas where digital twins are now applied. I mean, companies don't talk too much about it because it's a highly competitive area, but this is happening, okay? And just to illustrate the gravity of the problem, let's talk about the game of life, which you have probably heard about, a very simple cellular automaton where cells duplicate under certain kind of circumstances or die. And this is based on 3 simple rules. Now, if you would take an AI system or machine learning and train it on data produced by the game of life and try to figure out what the 3 simple rules are, you will most likely fail terribly. It's easy to produce the data, but it's difficult to extract the rules that produce those data. I mean, machine learning can be very powerful, but it has fundamental limitations, in particular when it comes to complex systems. I've also pointed out some time ago that we're coming from times where we didn't have enough data to take good decisions in many areas of life in politics. And now, of course, in this big data age, we can take evidence-based decisions. That's a good thing. Processing power is increasing at least exponentially. Data volume as well, growing even faster. And that constitutes a problem because we cannot process all the data that is being produced. And in fact, the gap gets larger. So there's more and more dark data that will never be processed. And that implies that you need to know which is the important part of the data to look at with your algorithms. That cannot be automated necessarily. And so we need science in order to do that. It creates a paradoxical situation where even though we have the best technology ever and more data than in the entire age of history, in fact, in 1 year, we're producing as much data as in all years before in human history. Despite this, the knowledge gap, in a sense, the dark data share is increasing. Plus, as we go on networking the world, this creates increasing complexity, and that complexity, I think, grows faster than exponential. I would assume a factorial relationship, and that overtakes even those exponential curves, which means that we would lose control of the system, even though we have more data and better technology than ever. And we need a new control approach. Fortunately, there is one, which is distributed control. And I will talk about that because this has a lot to do with how self-organization works. Now, I mentioned complex dynamical systems. I don't know why this movie didn't play. It's a pity because it's funny. So all these simulations are based on one set of equations. We just change parameters a little bit and you see that this produces very different behaviors. As an example for sensitivity of complex systems. Complex systems are in many places, turbulent fluids, traffic flows, large supply chains, social, political, economic, and ecological systems, financial markets, group dynamics, crowd behavior, and so on. It's not like this is a very special case of something we don't need to care about. Just on the contrary. Those complex systems have limits of predictability. We know that from weather forecasts. It cannot be done for 100 years or even a year or even a month. And even if you would have 1,000,000 times as much data as we have today, this wouldn't fundamentally change because we know that weather forecasts are based on fluid dynamics or gas kinetics. And those systems can show turbulence, and turbulence is mathematically understood to that extent that we know that there's limited predictability, fundamentally. Okay? And a similar phenomenon is deterministic chaos. Similar in the sense that also after some time things are often not predictable anymore. This is a very simple system called Lorentz attractor. You see it's three differential equations that are coupled with each other in a nonlinear way and produces amazingly strange attractors, as they're called. Plus, even if we start in almost identical initial conditions, could be a difference kind of in the 10th digit after the comma, perhaps. So really small difference. After some time, things would develop differently and become unpredictable. And this is called the butterfly effect. I openly admit it's very difficult to imagine this. But what it says is that if there was a butterfly and you had a deterministically chaotic system and the butterfly flapped with the wings, that could change the outcome after a long enough time period. And there are even mechanical systems that have similar behavior. Already the double pendulum behaves in unpredictable ways. The pendulum is a very boring mechanical system. So if you put two pendulums on top of each other, connect them, why would that behave suddenly in a very interesting, unpredictable, chaotic way? But this is how things go. So there's three pendula actually behind each other. In the beginning, they're just the same. Very little difference, but over time, we'll see that those three double pendulums with almost identical initial conditions would eventually behave very differently. Also, surprisingly, almost the entire phase space over here is being covered by the motion of that double pendulum. It's already here where your super duper computer gets to its limits. Now, suppose you would use that supercomputer to simulate the entire world and predict the future. Is it possible? No, of course not. Still, countries invested billions in order to try to do that. And of course, there's more behind it because not only do they want to predict things, they also want to control everything. Now, talking about control, even if you have this simple nonlinear coupled differential equation, which describes simple ecological systems, in effect, the so-called creative prey equations, like foxes and rabbits, for example, and assume there is a hunter that wants to get the system into some healthy equilibrium, whatever that means. We try to get over here. In fact, what happens is something very different. So these systems are very difficult to control. If you start controlling them, you would get a different outcome from what you expect to happen and what you want to happen. And if there are many different such systems coupled, like many driver vehicle units, in this case, drivers are supposed to drive in a circle smoothly without producing an accident, but also without producing a traffic jam, and they fail miserably, right? It should be an easy task. They have a driver's license, a good education, they have modern technology, well controllable, they have perfect sight. Nobody wants this traffic jam to happen, and still it happens. Why is this? Because there is systemic instability. Even if you could look into the brains of people, you may see it happen, but could you prevent it? I doubt it. It can be prevented, though, not by centralized surveillance, but in a very different way. So what you do over here is we simulate stop and go traffic as we've just seen it. There are mathematical equations that allow to do that. Not too complicated, actually. Just our coffee meter. It's a measurement of discomfort, sudden changes in acceleration. Now we get really annoyed about this traffic jam. We take a helicopter to see why is this happening. What we see is not only the beautiful Alps, but also there's an on-ramp. And here some cars are trying to get into the freeway, and that produces small perturbations of the flow on the freeway. Those are being amplified, and eventually this produces stop-and-go traffic. Now, assume we could equip the cars, all of them, or a certain percentage, like 30%, with traffic assistance systems, sensors that measure the distance and relative velocity, like lasers, for example, or radar sensors, and then use this data to have the cars drive automatically in certain ways. And as you could see, the traffic jam did go away, even though the inflow stayed the same. We could dissolve the traffic jam just by changing the interactions between cars. There's no central control of the cars over here. This change in the way of interaction is called mechanism design, and this kind of a key discipline of complexity science. What we do here is we do real-time measurement, like with this laser or radar sensor, and we feed it back in real time to change the interactions a little bit. Okay, and this is not just theory, you know, we actually made experiments, not only on test tracks, actually. So it doesn't, where's my mouse? It's on strike. Huh?
It's on this screen, it's on that screen.
Okay.
Now we have
Okay, so this was just one of the experiments, but in fact, those cars with our driver assistance system that could potentially dissolve traffic jams, this was being tested also on real roads. Before people were talking about Google self-driving cars and things. That was back in the early 2000s, like 2005, 6, 7. So what we can say is with the Internet of Things, I mean, measurement sensors connected to the Internet, we can now make self-organization work 300 years after Adam Smith introduced the concept of the invisible hand. Complex dynamical systems tend to self-organize. It means, in a sense, to do what they want. The question is, what do they want given certain kind of interactions? Establishing suitable interactions will produce desirable outcomes by itself. Very efficient. You don't have to force it. You know, just need to have the right interactions in place. So, you know, we have to figure out as scientists what are the interactions that produce the outcome that we'd like to see. Now, importantly, our brain, our immune system, ecosystem, societies, and much more are all complex dynamical self-organizing systems. Living systems, the wonder of life, are based on self-organization. And there are many interesting phenomena. And one that I got fascinated by is the lane formation. You can see that the oppositely moving pedestrians are separating into separate lanes of uniform walking direction. Is actually related to my most cited paper. And here's one of the figures of that 1995 paper. And then eventually we moved on to understand crowd disasters. Things got published in Nature and other high-level journals. And after some time, we also got some data to look into and we understood the courses of crowd disasters much better. In fact, crowd turbulence turned out to be one of the sources of crowd disasters. It's a physical phenomenon. There are other phenomena which are interesting, such as spontaneous stop-and-go waves that would occur also in pedestrian crowds under certain kinds of conditions. And it was pretty surprising to be discovered in crowds under certain kinds of conditions, very high density. And this understanding, on the other hand, helped to come up with measures to make, among others, the Hajj safer. But the insights are also being used now to improve other mass events and make them safer. One of the interesting phenomena is a so-called faster is slower effect. If people run towards the door and push, it will slow down the evacuation. You could also frame it as slower is faster effect. So people don't run, don't push, they will evacuate faster. And then eventually companies got interested in that. Companies had also problems with throughput, including the computer chip producing company Infineon Technologies that was in my Dresden times. So they had basically this wafer producing unit with many different kind of chemical bases and water vessels that the silicon wafers had to go through in order to etch out the structures that would eventually be the circuits that you do computations with. And they were trying to optimize the parameters to optimize the throughput, and you can see that the predictability was very low because there was a large variation if you changed a parameter a little bit. So it was basically unpredictable what throughput they would get if they changed the parameter. They couldn't just measure all the parameter combinations. So they didn't know how to really get this machine to high performance. And we told them, relax, apply the slower is faster effect, don't try to rush the process as quickly as possible, because that produces a problem that this so-called handler, this is or gripper, which moves around the different parts in the machine, that would be overloaded if we push the process quickly, because there would be different processes asking to be taken care of at the same time. And then there is a conflict of interest, and it would be poor quality produced and basically throw it away. So we said, slow down the processes so we would not have so many conflicts for that gripper. And this, we changed basically from here to there. And the throughput increased by more than 30%. They were totally happy. They made a lot more money. We got nothing, but at least we have this wonderful graph over here. So it's good enough for a scientist, right? Okay. Now there's a new paradigm basically that I would like to advocate, which is to go from control to coordination. And we have applied that actually in the context of traffic control. What we observed among pedestrians at bottlenecks is that there would be oscillatory flows. Even though there's no traffic light, there's no police, there's no prescription how people would have to pass the door. There's a pressure principle that makes the crowd move through that bottleneck in an oscillatory way. We thought, that's interesting. Couldn't we define a pressure principle for intersections of roads in such a way that this would produce self-organized oscillations, and we could use that to define traffic lights? That means could we basically have the traffic flows control the traffic lights rather than the other way around? That was the idea. And so, of course, everyone wants to have green waves, and this is just the case for square grids, but you can see over here that coordination is possible, and this is what we like to create. Now, how was it created? Now, one of the aspects was that we were not just assuming measurements of the outflow, but also of the inflow into a road section. So that allowed us to do short-term prediction, really short-term. But it's already allowing for some improvement. And then we were comparing 3 different control approaches. Left, the traffic control center as we have it today costs millions every year. It's like a benevolent dictator. That's, I guess, how they see themselves and collect a lot of data from all over the city. And then they're trying to come up with an optimal control scheme and impose it on the city like a dictator, you know, to the best for everyone, they would think. And the question is, how well does that really work? Given that traffic light control is an NP-hard optimization problem. I mean, it cannot be solved in real time, even with a supercomputer. Okay, so they need to make some simplification or approximations. Then what we do over here, we follow the idea of economics. Each intersection acts like Homo economicus, like totally selfish. They try to optimize travel times based on the inflows on the neighboring roads. That's it. They don't care about any other intersections. They don't care about coordination with anyone. Just every intersection locally tries to do the best. Okay. And then here we do the same thing, but long queues will be cleared before we go back to travel time minimization. So it's other regarding to with regards to neighboring intersections because it avoids spillover effects. So we would think this should be the best because it coordinates intersections. That should be the second best, and that friendly traffic light control and cares about everyone else, you know, that's probably going to have some deficits. Well, it's very different, actually. Red curve is for the traffic control center. As traffic volume goes up, capacity utilization, the queue lengths behind the red line also increase. Okay, nothing surprising so far. Now, how would actually, how would the selfish optimization, Homo economicus approach perform? This is the curve over here. The C is much better for low traffic volumes, but then suddenly queue length explodes. And so we can say over here, Adam Smith's invisible hand works, self-optimization is much better, but over there it's much worse. It doesn't work. But the third approach, the other regarding one, is actually better all the way. Okay. And then the question is, does it really work in reality? And in fact, this was being implemented in Lucerne, half an hour from here. My previous PhD student who worked on that traffic light control, the self-control, did that together with the previous manager of the traffic control center of the city of Zurich. They created a company, and there were measurements before they implemented their self-control scheme and after. And these are the improvements in terms of performance, and waiting times could be reduced considerably for all modes of transport. And here you can see how it looks like in terms of the congestion patterns. This is what they had before, a green wave, but still a lot of waiting time in red. This is the self-control approach. You see much less waiting times, much less red. Okay. So more green for everyone was kind of the slogan that the city of Lucerne used. which seems an impossibility, but just means that green time was not wasted when it was not needed, okay? It turns out to be also good for the environment. Climate-friendly traffic light control. And then we had articles about this, we cannot control everything top down. In fact, it was just the other way around, you know, like in a sense, traffic light control today is like a dictatorship amidst democracy. We came up with a bottom-up democratic traffic light control. And there were large articles on the newspaper, the revolutionary idea, it said, but perhaps it was too revolutionary because some little articles said why they didn't do it because they were afraid it would work too well. What can you argue against that? Okay, so basic democracy for traffic lights. And that was really kind of shattering the way people were thinking about how we had to control the world in order for it to work. You know, Ampelsteuern sich selbst, you know. This apparently is kind of really turning the world upside down. You know? But the fact is, informationally assisted self-mutation works well, is efficient and resilient, can handle reasonably large deviations and perturbations, is compatible with freedom, democracy, and human rights. So why don't we do that everywhere, you know? In particular, how can we use it to improve democracy? I've been working on this subject at least since 2015. I do think that democracy is about enabling distributed knowledge and collective intelligence. So we were asking the question, how to build digital democracy, how to bring the best ideas of many minds together. And all of that, according to our point of view, has to do with collective intelligence. And collective intelligence is fascinating because if you combine one solution with solutions that perform worse, it often creates a better solution, which is very puzzling. So diversity is important for performing better. Combining different solutions is key. And for this collective intelligence or wisdom of crowds, as some people call it, to work, you need to apply a certain kind of rules. In phase one, you would have independent information and solution search. Here, people should not be manipulated and influenced in their search for information solutions. Doesn't exist anymore in modern time internet because everything is increasingly personalized, which means manipulated. Diversity is really important for this step. And then only then people sit together, exchange information, share opinions, and discuss. There's a deliberation process. And as a result of that deliberation process, there will be integrated solutions. And after that, you would vote on those integrated solutions, which are typically better than the single solutions that may have been produced by experts. Okay, so voting is a key element over here. Now, importantly, however, what we found out is that majority voting, even though it's the most common way of voting, is among the worst voting methods. There are various issues. One is the worry about the tyranny of the majority. That means that a small majority basically determines what everyone has to do. The other thing is there's no fairness, in particular, no spatial fairness. So talking about spending money in a city, And suppose there are different projects, and then we vote about these projects. It's no surprise that the central districts will win, because these are typically the districts that have most people living there, higher houses, more density, more people voting. So basically the periphery gets forgotten, and then you get banlieues and social problems, and everything according to democratic rules, but only according to the majority rule. Turns out they're better rules. And so if we are looking for ways to improve and upgrade democracy, then we need to look into what can we change. And so voting basically has at least two elements. One is called the voting input, which measures or tries to measure your preferences, but in a simplified way, typically with a paper ballot or something like that. You have not many options to express yourself. But there are different ways of measuring preferences. And then it goes into a ballot box, and then there is a vote aggregation, which determines the democratic outcome. Okay? Different ways to do the voting input and different ways of vote aggregation. And in order to make experiments, scientific experiments, we created an app that allowed to experiment with different kinds of voting rules. And I'll show you just a few of them. Like the most common voting input is based on approval voting, where you can basically check boxes. Yeah? So you can select candidates or projects or whatever. And this goes then into the ballot box. Now, a bit more differentiated is combined approval voting, where you can either approve, abstain, or disapprove. Again, goes into the ballot box. Then there's ranked voting. In ranked voting, you rank the options according to your preferences. Okay? And further on, there is cumulative voting, where you have a certain number of points which you can distribute over different options. And this way you can express the intensity, how much you like a certain project or a certain option, okay? These are just some examples for different voting inputs. And of course, then you can make experiments. What are the advantages and disadvantages of different voting inputs? Same thing for the aggregation procedure. Typically, we do majority voting. And this means basically those options with most votes will make it. But it totally ignores normally the costs of those different projects, say. Right? And those can be very different. So another way of determining the outcome is to calculate the number of votes per cost. And then it turns out different projects would be selected. And then there is again another approach, which is equal shares, where basically you get a virtual budget that you can distribute over the different projects, and all the projects that get enough money to be realized, they will be implemented. And then the money not used will be redistributed over the remaining projects. Now, the important point I'm trying to make is that there are different democratic voting procedures, and they will have different outcomes. And this is what often happens with majority voting. There is one project that basically eats up most of the budget, and for everyone else, there's basically nothing left. I think we all know that situation. While there are other approaches that actually distribute money over many more projects. And perhaps that's a way to make more people happy. And perhaps that's not a bad idea. Okay. Now we have really applied that. A method that's called participatory budgeting, which is now very common, a favorite approach to make procedures more democratic. Barcelona is one of the cities known for that. And basically, the city puts a certain budget on the table and says, hey, citizens, this money is for you. You come up with ideas and projects, and then you vote, and then we implement what you voted for. You're the boss, basically. And we did that in the city of Ara, a bit smaller than Barcelona, but we start in the beginning, like A, and we end at Z, like Zurich, like is not a bad combination, I think. So basically, this was announced, and there were all sorts of brainstorming sessions to mobilize collective intelligence, right? There's citizen workshops where deliberation was going on. We used Mentimeter, among other tools, to collect the ideas that people came up with in the brainstorming sessions. There's some of the people involved in that project, supported by the SNF. And yeah, here you can see some of the keywords that seem to matter for people in this connection. And after some time of brainstorming, people had some ideas, and those ideas were put on the map with sticky notes in the places where those projects should be realized. And of course, over time, those ideas had to be worked out and tested for feasibility and how serious they are, and where people are committed to implement that, and so on. So basically, the 161 initial ideas were eventually narrowed down to 33 alternative projects that were considered to be feasible, and 32 of them fit on this slide over here. People did vote. It was announced also in bus stations and many other places, and we made sure there was transparency about the procedures, what kind of democratic procedure we would apply. The cumulative voting was explained, and it was also explained that it mattered not only the number of votes that a project could accumulate, but also the cost. And that made basically the proposers careful not to go for the maximum amount of money, but for the amount of money that they thought was needed to implement the project. So projects were presented cheaper than in other cities that didn't apply that procedure. And then the voting happened. Oops, sorry, I was a bit too fast. Okay, now people voted, and this is the outcome. And you can see that overall, those projects were selected that had a particularly high number of votes as compared to the costs. Things are a bit more complicated in this proportional fairness approach, but I think this is a pretty clear picture over here. Also, voter satisfaction was pretty high. Spatial fairness was high. You can see, while majority voting would really concentrate all the money in the city center, the proportional fairness distributed the money over basically all districts of Aarau. Instead of 7 projects that we would have had for majority voting, we had 17. So it was a lot more groups could be given some money to realize their projects of interest. So it was a lot more inclusive. We had a better gender balance than for referenda. We had a better age distribution than for referenda. More younger, more elderly people were involved, more foreigners. So it was really appealing to people. They were engaging, and so we can say democracy can be upgraded. We can have more projects, more resourcefulness, more participation, more inclusion, more transparency, more trust, more satisfaction, and more fairness. And I think we can call this better than optimal because it's not based on optimizing a one-dimensional utility function, which would otherwise be the basis of optimization. Then the question, can economy be upgraded too? And in fact, it can. Eleanor Ostrom made really some very fundamental contributions showing that self-governance can be efficient if one applies proper design principles. So based on all this, the conclusion is that we should combine synergy and cybernetics in a way that supports bottom-up self-organization, that assists it, but allows for it. We studied this in connection with coordination, cooperation, collaboration, co-evolution, conflicts, crime, pedestrian flows, traffic congestion, crowd disaster, economic systems, and more. It works. And about 10 years ago, or even a bit more, the US government said, the US needs a future ICT program, a merger of information and communication technologies, complexity science, and social science to create socially adaptive, self-organized ICT systems. The result was future ICT was turned down, and this was not implemented, not even in the US, it seems. Instead, something very different happened. So the idea was, what would happen if one fed all the data of the world and brute force into a huge super duper AI system, much bigger than you can imagine, bigger than what Sam Altman has on stock, and allow it to run the world, or would allow somebody to rule the world with that tool. Is it a great or a small idea? I think it's not a big idea, because that's what you do if you don't have a better idea. Like just you do the biggest thing that can be done technologically with all the money and all the data and all the chips you have. Okay. Anyway, if you have enough money and enough data and enough chips and so on, you can do that. And then basically, there is another version of it that which we implemented, which combines cybernetics and synergy into some cyber sim with a control room that tries to harvest all the data to control the city or the world. So it's a surveillance-based, data-driven, AI-controlled society concept. I'm not making this up. I mean, if you just read enough, we'll figure out this is what's happening. Among others, Edward Snowden has informed us about it. There was an article, among many others, in The Intercept called Profiled, which was about the profiling of people, like you and me and everyone else. And so basically, using internet data, they were trying to reconstruct everyone's personality in quite some detail, a lot more detail than this figure shows, of everyone, without their knowledge and agreement. And how does that work? Among others, with cookie trackers. In the meantime, I think you know that some newspapers have about 100 or even several hundred companies that track cookies while you surf their web pages. What are they doing with all that data? Among others, they're so-called A/B tests. So web pages are being personalized. You get personalized ads, but not necessarily only. You could personalize everything. headlines, photos, how things are arranged on the page, all sort of things could be personalized, and they could basically check out how you respond to that different configurations. And particularly could check out how to make you do certain kind of things, like buy a certain product or so. So as I said, it's called A/B testing. And so basically, you deliver input, data, information input, to make people respond. You measure that, that's the output. That goes as input into the machine learning AI system. That then produces, again, some output that would be the input for your behavior. And this way, they basically check you out until they know who you are, what your personality is. And this creates eventually digital twins. And the attempt is basically to create digital twins of body and mind. It's one of the reasons for the mass surveillance that we have. They're working on this already for at least 15 years. Digital twins of the world and its people is being used in particular for warfare, for psyops, manipulate people like you and me, but more even politicians, of course, presidents of countries, people who should download a virus on their computer to basically compromise your computer and allow to get some data and so on. So then another thing that happens is targeting. That's behavioral manipulation. And all of you are being targeted. And that's easy to do if you have a digital twin of somebody. Then you know who the person is. What are the strengths and weaknesses? What are the desires, the hopes, the fears? And that can all be used basically to trick people, to manipulate them. And there's even a so-called documentary, not even too good, on Netflix, but it at least gives you some idea of what they're doing. So there's all that surveillance or spying data about you. It's being used to manipulate you in a targeted way, in a way that is often hard to detect. You would not necessarily notice that you have been manipulated. And it has been used for all sorts of things, including attempted election manipulation. Cambridge Analytica basically revealed this scandal. It's not the only company, but that company tried to manipulate more than elections in more than 60 democratic countries. That means for at least a decade, if not more, we didn't have non-manipulated elections. Tristan Harris, who worked in a so-called control room of Google, he gave an excellent TED talk, and he even calls that mind control. So how a handful of tech companies controls billions of minds every day. And these are spin-offs of even more powerful technology that the military uses to manipulate you. It's weaponized propaganda AI that knows you better than yourself. Our brain is a wonderful organ. It just needs 100 watts, like an electrical bulb. It can do so much more. No supercomputer is by far as efficient as our brain. Our brain simplifies things, and that's why it can be hacked. And secret services, we also know since Edward Snowden, have been basically creating hacks, algorithms to hack you for all those different biases of our brain. So AI is being used to hack you in a sense, right? And so basically now, I told you, they're not only trying to predict the future, in order to make it more predictable, they're trying to control everyone. So we would do what that prediction says. In other words, they would try to come up with an optimal solution for the world, but everyone has to play according to that game. And they're trying to make that happen. Of course, it doesn't happen 100%, you know. But in a sense, you're trying to play robot chess where we are the pieces of that robot chess, you know. Like, perhaps you know this book, The Grand Chessboard. It's kind of, they're using AI to, you know, make things happen. Okay. Things go so far that some people think it would be a great idea to have a post-choice society. Now, if AI systems would just know everything about everyone, why should we even ask them? Why should we even vote? You know, it's a waste of time, according to them. But how well would such a system work? You know, I mean, they probably think they have a great idea. And they just try to make the world efficient and optimal, right? So let's assume for a moment that we would use all that surveillance-based data to basically optimize the world like a benevolent dictator using the biggest AI system that somebody can build. Is it going to be a good thing? Is it going to create a paradise for everyone? Or is it being a dystopia? Well, a benevolent dictator certainly wants things to be plannable, predictable, and controllable. That's already not well compatible with democracy and freedom, but it would create a better world for everyone. Then perhaps you would say, okay, that's fine. But does it really create a better world and a better world for everyone? So what would a benevolent dictator probably do? Would first determine the individual utility function. What do you want? Everyone wants. As I said, with all that profiling, they're trying to do that. Everyone's utility functions are different. Everyone wants something else. So unfortunately, they need to determine an average utility function. Why? Because if they want to optimize the world, you need to have a goal function. The goal function needs to be one-dimensional. Otherwise, you cannot make those operations like this is better than that. This is greater. This value is greater than that. Okay, so for that one-dimensional goal function, you need to average all the utility functions, and then you would look for the optimal solution to this average utility function and implement it like a dictator. Now, unfortunately, an average utility function serves many people not so well because we're not average people, sometimes even quite badly. You know, it's really like this traffic control center that was coming up with an optimal control for a situation, for a typical situation that, however, never occurs. So goal functions are one-dimensional and tend to oversimplify our needs. Societal needs are multidimensional. We want to have more prosperity, more sustainability, more health, more resilience, more education, more culture, more everything in a sense, you know. And even though data-driven optimization, as I tried to explain, is not expected to work well enough for societies, there are even more extreme forms of this surveillance-based AI-controlled approach in the pipeline. Now comes some technology that's not so well known, like Li-Fi. It's kind of the follow-up of Wi-Fi. It's kind of light-based data transmission. It would use technologies such as LEDs. One LED can, I think, transmit 8 megabits per second, quite a bit of data. Interesting technologically speaking. It would someday be built into our smartphones. There are already some smartphones that can do that. And then, you know, you would have to transmit all that huge amount of data via light, as I said, and there are satellites that do just that. And you need to have new kind of computers in order to process all that data. And that brings us to the quantum computers. Okay. And still not all. So what now follows, many of you may consider to be science fiction, perhaps shocking. This is a warning. But it's less science fiction than you would think. Because we are now approaching a time where we see technological convergence or converging technologies, where digital technology is being combined with nanotechnology, biotechnology, gene technology, neurotechnology, cognitive, whatever, computing. And so technologies that used to be separate are fused and combined with each other and miniaturized to a scale unimaginably small. Okay? And some people think this would also bring about eventually something that people call human-machine convergence. We would upgrade ourselves with, functionality that we can build in machines. And that has to do with transhumanism. And some people think basically transhumanist politics started back in about 2013, 14, 15. And just to give you an idea what some of the philosophy of transhumanism implies, there's the so-called transhumanist wager. And it says transhumanists must strive to achieve omnipotence. Okay, and so there's just one person who believes in that and has the power to decide what we do with technology, then what will happen? Basically, they would build a so-called Internet of Bodies. This is a Future Health Manifesto over here. So you read about the future of healthcare, deep data, smart sensors, virtual patients, that's the digital twins now, kind of different word. Internet of Humans, that's the Internet of Bodies. Now, back in 2020, the World Economic Forum told us the Internet of Bodies is here. Now, and tracking how our bodies work could change our lives, and surely so. So this is about in-body surveillance. How does it work? It's based on the Internet of Nanosthings, or Internet of Bio-Nanosthings. And so basically you expose the body to minute particles, not bigger than 100 nanometers, perhaps much smaller than that. Put them into the cells of our body. And then if you use the right kind of materials, you can interact with those particles through radiation. And thereby read out data about what happens in your body. Lots of data, okay? And this is in particular interesting not only for personalized medicine, but also for neuroscience and neurotechnology. So back in 2013, the Brain Initiative mission, also known as Obama Brain Project, was aiming to understand the inner workings of the human mind and to improve how we treat, prevent, and cure disorders of the brain. This is called the Brain Activity Mapping Project. And then if you want to know what this is about, it says, this is another scientific paper, nanoscience and nanotechnology are poised to provide a rich toolkit of novel methods to explore brain function by enabling simultaneous measurement and manipulation of activity of thousands or even millions of neurons, like a high-resolution EEG. We and others refer to this goal as the Brain Activity Mapping Project. Now, if you look for information, then you figure out that the prediction is that while we had a doubling of the amount of data within 12 months recently, it will be 12 hours soon. because of human brain indexing. So then they're not anymore just interested in what you're shopping and what your friends are and how much you earn and where you live. But, they're trying to figure out what you think. And some people are working on the idea of the brain cloud interface. Elon Musk obviously is one of the people interested in this. He's working on so-called brain chips, the Neuralink system. The question is, would you even need chips? Because there's also a possibility to use nanotechnology in order to read out data, as I said before. So if you look a little bit around, you will see brain reading tech is coming. The law, unfortunately, is not ready for this. Things are going further. So the idea is basically to spread dust, these nanoparticles, so they would be absorbed by brain cells, and then either by 5G, 6G, or by light, which is optogenetics, it would be possible to read out data from cells. So if you want to learn more about it, read about optogenetics. So now, this is totally fascinating, okay? There are papers in Nature series journals, eye level, about optogenetic control of RNA function and metabolism and switching of an RNA function by light. So here is an article by, I think, Reinhard Merkel. He was kind of one of the chief ethicists of the German government. And he writes, die Optogenetik erforscht Wege genetisch veränderte Nervenzellen über Lichtimpulse statt durch Elektrizität anzuregen. Genetically engineered or changed cells. And then you read this about human augmentation. It's a report by the Ministry of Defense, I think UK, together with Bundeswehr Office for Defense Planning. I really recommend you to read this. This will be eye-opening. Okay. And it's now getting a bit more philosophical, because now the question is, if you have all that technology, now could you build something like an AI god? And somehow I felt that this is what we're aiming for. I warned of that already back in 2013. And in fact, you could argue Google is trying to create that omnipotence that I've been talking about before. Like omnipresence, having internet everywhere. They were trying to build that, the Google Loon project. And Google Glass, Nest, omniscience, like knowing everything happens, probably also in this room, when even if you don't have a smartphone with you and talk to somebody else with a smartphone, they could know it. Google Brain and DeepMind, trying to create super intelligence. Google Calico, to be an emperor over life and death. In fact, the goal is to kill death. And even basically make people walk again who couldn't before. And so basically, yeah, they're working on all those omni features. And I've written several more articles to warn off such kind of omniscient, omnipotent AI data-driven concepts, including a science fiction, which, funny enough, is translated into Chinese. And a couple of years back already, you could read articles like this, AI God is here. And at that time, Elon Musk actually was slamming that proposal to create an artificial intelligence God, because he thinks that we should be very careful about artificial intelligence. He thinks it could be the biggest existential threat he thinks we're summoning the demon. All right, so I mean, many people are worried about AI. It's a wonderful thing. You can do really many wonderful things with AI, with big data, no question at all, you know. But you can also do terrible mistakes. There would be often unknown, unwanted side effects, and so are we making the biggest and most dangerous experiment ever in human history? That's the question. People are already worried about potential loss of millions of jobs, of mass surveillance, possible mind control in the future. I'm not saying it's working perfectly yet, but they're trying to make it work. Transhumanism, on all this, but I think perhaps we have even a bigger problem than that. So one of the ethical principles of AIs and other systems is non-malevolence. And my impression is that this actually does not apply to many of the data-driven digital technologies that are being worked on. Citizen sports, big nudging, Internet of Bodies, transhumanism, and so on. A lot of that appears to me like different forms of techno-totalitarianism. Trillions have been spent on these kind of technologies. The world's problems still haven't been solved. So do we have the right approach, actually? In a sense, they're trying to automate the world, to turn it into a machine, and I think it can't work. I've given some reasons why that can't work in the beginning. I give two more reasons here. The digital revolution has coupled local and global, removed separation in many respects. Pretty much everything has been coupled with each other. This makes the world behave differently, and many perhaps have not realized it yet. We just wonder why the world behaves in such a strange way, and there's so much stress in this world. Some of it is certainly related to that. So, however, all that too much networking, in a sense, can destroy the modular nature of the world and the related functionality that we rely on. This connecting everything with everything else increasingly, also through AI systems that learn about all the text, like ChatGPT basically feed in all the texts, you know, that you can get hold of. You couple all of that with each other. So what I expect is this will trigger tons of butterfly effects. And even worse, trigger all sort of tipping points. That means it's a recipe for disaster, I would say. You know, I've been warning of this. I recommended to take a different approach based on distributed control, bottom-up self-organization. Back in 2014, now people increasingly realize that this should have probably been paid more attention to. I mean, it's more than 1,000 citations, but apparently it's not enough. So in a sense, we must learn to now cut the Gordian knot. And so basically to get away from connecting just everything with everything else, to organize the world in a modular way. We have applied that principle in particular to organizing flows around the Gamma Bridge, and when it was applied, it worked very well. So we know the approach does work if well done. An even bigger concern is that through converging technologies, we couple pico, nano, micro with macro scales. You know that quantum physics behaves very different from classical physics, like mechanics, electrical dynamics. There's superposition of states, you know, Schrödinger cats, and all of this. Quantum computing is based on superimposed states and so on. So now, if you couple that with the macroscopic world, then intuitively, I would expect that we would see more quantum effects on macroscopic scales. And that would really make the world behave very differently in ways that are hard to predict. So before I told you what I would do to save the world, I think, it can be saved, not with the AI gods, according to my analysis, but it can be saved if you understand complex systems and self-organization and music well. This, I think, is a recipe to really change the world forever